Okay, guys, we're going to look at the homework questions for March 24th. These are the kind of extra ones that I inadvertently set. The focus was meant to be on forces and mechanics, but I got the questions mixed up in the assignment. If you were working off the PDF that I attached, it's all good. But if you went off just the questions, you probably tackled these two questions. It's my fault. But because you did it, I'll go through it anyway. It's all good. It's all revision. And even though it wasn't quite what I intended you to revise quite yet, but look, what can you do? So this is going back to calorimetry and heat transfer for this first one. And it's an experiment-based question. So let's have a look. In an experiment to determine the specific latent heat of fusion of ice, a student first crushed some ice, then dried it before adding it to warm water in an insulated copper calorimeter, recorded a load of data. Now, we'll get back to the data in a moment because there's a couple of traps there. But let's just deal with these kind of easy enough questions here. 18 marks for just a couple of questions on why she did it this particular way. So why did the student crush the ice? She crushed the ice so that the most surface area was exposed for heat transfer as possible. Why did she dry the ice? Well, she dried the ice because if the ice was, let's imagine that's just a block of your ice there, and if it was melting, some of that ice would be converted into droplets of water. Now, you don't want to have to take that into account when you're doing your heat transfer. You want the only heat going into the ice to be going into melting it, and then possibly heating up the water afterwards. You don't want to have to deal with water droplets in the mix at the start. So she dried the ice to make sure it was only ice that was added. How was the ice crushed? Well, a number of things. You could put it in a blender. You could hammer it up with a plastic bag and anything metal. How was it dried? Paper towel does the job. Why did she use warm water? Okay, she used warm water so that the ice would melt quickly and you get a noticeable increase in temperature. Why did she use melting ice? Okay, let's go back to our ice block again and imagine if that ice was at minus 5 degrees Celsius. It's going to take heat energy to bring that ice up to zero, at which point it can melt. We don't have to take that into account. So if we have the ice that's at zero, which is when it's melting, we know that it's at 0 degrees Celsius or 273.5 Kelvin, we know that we don't have to put heat in to bring it up to zero. So the only heat going in will be to melt it, the latent heat, which is the point of the experiment. Now there's 6 brief little questions, 3 marks each, 18 marks on a leave insert question without having to do any kind of data manipulation. Now the rest of it's going to be harder, but they're quite handy to get hold of. Okay, so always just, again, one of the trickier things with higher levels, they won't explicitly say, question 1, question 2, question 3 often. You'll have to just be kind of on the ball a little bit. Now to be fair here, they did 1, I. But just be aware, sometimes they can have a question and you can skip it without, paying attention too much. So make sure to read the question carefully. Okay, onto the bones of the question. Use the data to calculate the specific latent heat of fusion of ice. Okay, well, we'll look at the units and traps in a moment, but let's look at broad strokes what's happening here. Now, you don't have to draw a diagram for this, okay? They don't want you to draw a diagram. I am going to do it because I just want to get my head around what's happening. And it's a little easier if I picture it. So we've got a calorimeter, which is just a copper jar. We have some water in it. And we're going to add some ice in there. And of course we have a thermometer to keep track. Now this is not going to be any points, it's just to help us understand what's happening. So what is going to happen? There's going to be a heat transfer. Now the sum total of all the heat transfers are going to be 0 because we've insulated, or in this ideal system, whatever heat is lost by one thing is going to be gained by another. So let's think about what the heat transfers are going to happen here. Well, first off, the calorimeter is going to have an initial temperature. And as it loses heat, its temperature is going to go down. So its temperature is going to go down. The water that's contained in it is also going to lose heat. So its temperature is going to go down. The ice is going to melt. That's going to take energy. And then that ice water, its temperature is going to change and it's going to go up. Now, if you were in the habit of writing the heat lost by the calorimeter and the water is equal to the heat gained by the ice and the ice water, if that system works for you, go for it. I'm going to go with the total sum of all these energy transfers is equal to 0. Now, the reason I'm doing that is if you got trickier questions where you're trying to figure out the change in temperature, by doing it this way, the signs of the temperature changes will take care of any awkwardness. It just makes life a little bit easier. So I'm going to go with this system. So I'm going to go with, let's first off put the equation in, and then we'll look at units. So the change in temperature of the calorimeter is given by the specific heat capacity of the calorimeter, which is 390, but let's just go with heat capacity of the copper times the mass of the copper calorimeter times the change in temperature. We're going to do the same for the water. The heat capacity of the water times the mass of the water times its change in temperature. We should even just put a little C for there, W for there, plus the latent heat of ice, which is what we're trying to find. It's the mass of the ice times the latent heat. And you know what, just for our own lookout, that's what we're looking for. Put a little red box around it. Plus the mass of the ice times its change in temperature. And all of those should work out as being 0. That whatever heat is lost by one thing is going to be gained by something else, and overall it'll balance out. Now let's start up by bringing the thing we're looking for to the other side of the equation. So we have the mass of ice latent. If we bring it across, it's going to be minus. So the minus the mass of the ice times latent heat, which is what we're looking for, is equal to heat capacity of the copper, mass of the copper, change in temperature of the copper, plus heat capacity of water, mass of water, its change in temperature, plus mass of ice times its change in temperature. Okay, we'll do one last little bit of algebra before we look at our numbers and sub them in. We're looking for the latent heat of ice, so let's keep that on one side. On the other side, we're going to have heat capacity of the copper, mass of the copper, its change in temperature, plus capacity of water, heat capacity of water times the mass of water times the change in temperature of water, plus the mass of ice times its change in temperature. Oh, I missed out something here. Times the heat capacity of water, because that ice would have melted to become water. And all of that, just the algebra I'm doing here is bringing the mass of ice across and dividing it in, minus the mass of the ice, or mice. Let's be a little neater here. Okay, now that's our equation. Before we tackle it, let's just take a closer look at the units and the traps they're laying for us. I'm going to zoom in a little bit if I can. Hopefully this doesn't lose focus for you. Okay, so first things first, they give it to us in grams, we want it in kilograms. So we're going to have to convert all of these to kilos. And 1 kilogram is equal to 1,000 grams. So we need to just hop the decimal place over by 3. So first off, we'll just convert these into kilograms, and then we'll look at the next step of maths. So the mass of copper calorimeter is 0.0563 kilograms. The mass of the calorimeter and the water before adding ice was 0.1085 kgs. The initial temperature of the water and the final temperature of the water. Now, the temperature change is going to be in Kelvin. Now, we don't have to convert into Kelvin because it's just the temperature change we're looking for. And 1 degree Celsius, a change of 1 degree Celsius is equal to a change of 1 Kelvin. So we don't have to mess around with the 273.15 or anything like that, not today. So the initial temperature of change of water, let's look at the change of water, let's get that written in as well. So the change of the water, it went from 29.5, which is the final temperature, down to 8. So 29.5 minus 8, its temperature change was, its final was 8, initial was 29.5, so 8 minus 29.5 is minus 21.5 Kelvin. That's the change that the water experienced. And it's also going to be the change that the copper experienced because they're in thermal equilibrium. So they're the same. Finally, the ice. Well, the ice went from 0 up to 8. So its final temperature was 0. Its initial temperature was 8. So the change in temperature of the ice was plus 8 Kelvin. Final minus initial. Oh, oops, backwards. Final minus 0. That's where the plus is coming from there. Okay, so I might just rewrite these in neatly here for a second before we sub them in. Now, before we do that, though, we need to get everything together. Just isolate all your variables first. So what's the mass of the copper calorimeter? Now, they give us that. We've converted into units. It's into kilos, 0.0563 kgs. Job's a good one. The mass of water, a little bit trickier now because here's the mass of calorimeter. This is the mass of the calorimeter and the water before adding ice. So imagine that this is your calorimeter before, calorimeter with water. So the difference between these is the mass of water. Just find a calculator here. So let's go with 0.108.5 minus 0.0563 equals syntax error because you've done it wrong. Let's try it again. Mass of copper calorimeter from 108.5 minus 56.3. So in grams, it's 52.2, but we don't want grams, we want kilograms. 0.0522 kgs. There's the mass of water. Let's look at the mass of the ice. Similarly enough, they have the mass of the calorimeter and water after adding the ice. We have to subtract this 108.5 from this. So the final weight of the whole shebang was 122.9. Subtract the 108.5 for a mass of 14.4 grams. We want that in kilos, 0.0144 kgs. Okay, there's our masses. We're given the heat capacity of water is 4180 joules per kilogram per Kelvin. We're given the heat capacity of copper is 390 joules per kilogram per Kelvin. And finally, the two temperature changes. The temperature change of the copper and water, which is the same thing, of the water in the calorimeter, they both experience a temperature change of minus 21.5 Kelvin. And finally, the temperature change of the ice, it went from 0 up to 8, so it had a temperature change of plus 8 Kelvin. Okay, I think that's everything we need. So we have our calculation. We have all our units. We've converted for traps. Now it's just a matter of substitution and working it out. So you just plug in the numbers. So let's do so. Now if you want to just skip forward a moment or two in the video, no, actually don't. Stay with it for all the laborious stuff because you have to do it too. So the latent heat of ice is the heat capacity of copper, 390. I'm going to leave out the units for now and put them in at the end just for the sake of brevity. Times the mass of the copper calorimeter times 0.0563 kgs, times the temperature change of the calorimeter, which is minus 21.5. Signs are important here, keep them in. Plus the heat capacity of water, 4180, times the mass of water, 0.0522, times the temperature change of the water, which is minus 21.5, again, minus is important, plus the mass of the ice, which was 0.0144 kgs. Do you know what? That's a bit messy. That's frustrating me. Let's just do it on the one page. 390, 0.0563 times minus 21.5 plus 4180 times 0.0522 times minus 21.5 plus, now, 0.0144 kgs was the mass of the ice, times its heat capacity, which is 4180, because it's time melted to become water, times its temperature change, which is 8K. All this divided by the mass of the ice, which is 0.0144. Okay, now it's just a matter of like being disciplined with the calculator, making sure you don't make any mistakes. Oh, speaking of which, that should be minus. We're going to divide it by minus 0.144. So let's deal with the top line first, just even on the calculator here. We have 390 times 0.0563 times minus 21.5. And then we're going to add that. I'm going to use brackets here to make this a little bit easier. 4180 times 0.0522 times minus 21.5. Now we're going to add that to this set of brackets. 0.0144 times 4180 times 8. That gives us the top line of our calculation, minus 4681. And we're going to divide that by the minus 0.0144 to hopefully give us our latent heat diffusion of ice, which is 3.25121 joules per kilogram. That's the latent heat diffusion of ice. So 3.25 by 10 to the 5 joules per kg. Okay, quite involved, quite tricky, and a real blast from the past, which you haven't been studying calorimetry, it might bite you in the neck, so just make sure to be going over it. Last part of that, why would using a very large mass of water lead to a less accurate result in this experiment? Well, if you're trying to heat, if the heat's coming from a large mass of water, you're going to get less of a temperature change overall. It's going to be less easy to measure. You're going to have a greater percentage error because it's spread out over a larger mass of water. Okay, fairly involved experiment question there. They really make you sweat for the last 22 marks. The first 18 were okay. Now on to another experiment question, which again I inadvertently said. Now the tricky part here is this is an experiment we haven't had a chance to do yet, so it's going to be like an imagination Christmas. But let's have a gander. In an experiment to investigate the variation of resistance of a thermistor with its thermometer, a student measured its resistance at different temperatures. The table shows the measurements recorded. Draw a label diagram of the apparatus used. I cheated here, lads. I drew it out earlier just for the sake of brevity. What we've got, a water bath with a heat source. It can be a Bunsen burner or an electric plate. Electric plate is what we're going to use. And we put our thermistor into a test tube filled with glycerin, or we'll probably use vegetable oil if we can't get any glycerin. A thermometer to keep track of the temperature of the water, and has to be connected to an ohm meter. Now you can also say that that's a multimeter set to measure resistance, but you got to be specific here to measure in ohms, which is what we used. Now, let's see what's going on here. So as we heat this, the water is going to increase its temperature. The oil and the water, if we heat it slowly, will be in thermal equilibrium, so the temperature of the oil will be equal to the temperature of the water. The reason we use the oil, that's probably going to be a question in a few minutes, but the reason we use the oil is it doesn't conduct electricity, it's a good thermal contact, and it doesn't have any impurities in it. If you use water, you'll often get little bubbles of air forming, and in addition to impurities, which throw off your calculations. So let's get back to the actual question. Sorry about that. Draw a label diagram. Done. Okay, make sure you label everything, which I think I've done here. I haven't labeled the leads, and I haven't labeled crocodile clips, which I should have done. My bad. Let's add them there. Croc clips. Okay, how is the resistance measured? The resistance was measured with an ohm meter or a multimeter. Describe how the temperature was varied using a Bunsen burner or an electric plate. So again, quite a handy 21 marks for the diagram and a couple of brief bits of explanation. Now they're going to make us work for the rest. Use the recorded data, plot a graph to show the variation of the resistance of a thermistor with its temperature. Now again, I cheated a little here, guys. I've done it ahead of time. If you want a video on how to do graph work, check out the other one on mechanics. But the short version is make sure that you've got units on there. So here I've got the change in temperature in degrees Celsius. You don't really have to convert it to Kelvin. You can leave it in terms of Celsius because later on they're going to ask us to do a calculation based on 45, 35 degrees Celsius. Have your resistance on the y-axis. Just make sure that you've got enough room to accommodate all of your values. So the trick here is to think about what is the largest value you have to accommodate. So in terms of degrees Celsius, it's 80 degrees Celsius. And in terms of ohms, you have to accommodate a maximum value of 2000 ohms. So then you have to decide like how many each box represents. I went with each big box representing 200. That way I could fit in my resistance on the y-axis. And on the x-axis, I went with a temperature increase, which is 10 degrees Celsius each time. Quick note here, this 0 Celsius, remember that's not absolute zero. That's not 0 Kelvin, that's just 0 on the Celsius scale. Okay, so you plot your points and you get this nice smooth, smoothish in my case. I went a bit wobbly there. Nice smooth distribution. The lion's share of the points here is just for doing your graph work and doing it neatly. So take your time, do it correctly. Don't rush it. Now, use the recorded data, plot a graph to show the variation. Done. Use your graph to estimate the average variation of resistance per Kelvin in the range of 45 to 55 degrees Celsius. Okay, so let's take our two readings at 45 and 55 degrees Celsius. Find my ruler. So drawing up at 45. It's useful to draw this on the graph to show them where you got your numbers from. So drop it vertical 45 and 55. And let's see what readings we get there for resistance at those two places. Okay, now I'm going to draw on my graph just for the sake of brevity. No, that's a bad example. Let's not do that. Okay, so at 45 degrees Celsius, my reading was, let's call that 580. Let's call it 580 ohms. And at 55 degrees Celsius, let's call that just shy of 300. Let's call it 290 ohms. So over 10 degrees, the difference in resistance was, let's see, 580 minus 290 divided by 55 degrees Celsius minus 45 degrees Celsius. So you've got a difference over, at 10 degrees Celsius, there was a difference of 290 ohms. And the question they're asking is the variation per Kelvin. So per 1 degree Celsius or per 1 Kelvin. So 290 divided by 10, that's 29 ohms per Kelvin. Okay, you might have a little bit of variation on your graph depending on how you did your curve, but it's usually plus 3 or 4, depending. Let's presume that I'm correct. I think it might be closer to 30. Okay, in an investigation, why is the thermistor usually immersed in oil rather than water? For good thermal contact, no impurities, oil does not conduct electricity while impure water does. Right, guys, quite a mouthful there, a lot to take in. Hopefully that was useful. Keep trying the questions and let me know if you're stuck on any, okay? I'm going to stop this video before this thing crashes out. And as I say, ask me if you've got any questions and I'll talk to you soon. Bye-bye.